In this video, we will discuss about the algebraic operations on vectors. Scalar multiplication. Multiplication of a vector with a scalar, or simply with a number, is called scalar multiplication. Let us assume a vector, A, having components a1, a2, and so on, an. When we multiply the vector, A, with a scalar alpha, it will be multiplied by all the elements of the vector. In simple terms, if we multiply a vector, A, with number 3, then the result will be 3 times the original vector. It means the length of the resulting vector will be increased 3 times that of the original length. If we multiply a vector with a scalar having negative sign, then also we will apply the same procedure. But the difference is, we need to change the direction of the vector to exactly the opposite, or 180 degrees away. For example, if we multiply a vector, A, with -1, then the result will be as follows. Vector addition. Let us consider two vectors A and B. Where a1, a2, and so on an are components of vector A, and b1, b2, and so on bn are called components of vectors B. When we add two vectors, the corresponding elements of the vectors will be added to form a resultant vector A plus b. The resulting vector can be drawn from the starting point of the vector A to the end point of vector B. The vector addition can also be represented as the diagonal of a parallelogram. Vector subtraction. Vector subtraction is nothing but adding one vector with a negative of another vector. For example, if we subtract the vector b from vector A, it can be written as follows. And the result can be drawn just like in addition case. There are two methods to multiply one vector with another vector: dot product and cross product. Dot product. The dot product is also called a scalar product. It is an algebraic operation that works on two equal-length sequences of numbers and returns a single number. The dot product of two vectors, A and B, is denoted with a dot b. Algebraically, the dot product is defined as the sum of the products of the corresponding elements of the two vectors. Let us assume two vectors, A and B. The dot product of two vectors is represented using sigma symbol. Here, sigma denotes summation, and n is the dimension of the vector space. For example, let us assume two vectors, consisting of 2, 3, -4, and 5, -1, -1 respectively. The corresponding elements, in both the vectors, gets multiplied. The result will be a single number, 11. Geometrically, the dot product is defined as the product of the magnitudes of the two vectors, and the cosine of the angle between them. If the angle between two vectors is 0, or 180 degrees, then the dot product is equal to the product of the magnitudes of both the vectors. If two vectors are perpendicular to each other, then the dot product of the two vectors is equal to 0. So, we can say that the product of two unit vectors, which are along the same axis, is equal to 1. And the dot product of two unit vectors, which are perpendicular to each other, is equal to 0. Cross product. It is also called as vector product. The cross product of two vectors, A and B, is denoted with a cross b. The cross product of two linearly independent vectors, A and B, is a vector that is perpendicular to both A and B, and thus normal to the plane containing them. We can also denote this with Fleming's right-hand rule. Let us assume two vectors, A and B, which are represented with standard basis vectors I, j, and k. Algebraically, the cross product, a cross b, can be written as. Geometrically, the cross product is defined as the products of magnitudes of the two vectors, and the sine of angle between them. If two vectors are perpendicular to each other, then the cross product of the two vectors is equal to the product of the magnitudes of both vectors. If the angle between two vectors is 0 or 180 degrees, then the cross product is equal to 0. As we know, the unit vectors I, j, k are along x, y, and z axis respectively. The cross product of unit vectors is as follows. If we change the order of I, j, k other than a circular shift, then we get negative signs for the result. In the same way, the cross product of two unit vectors, which are along the same axis, becomes 0. The magnitude of the cross product is interpreted as the area of the parallelogram, having a and b sides. In this video, we have discussed about the algebraic operations on vectors.